Hi everyone. Today we will be kicking off our 8th traffic webinar, which is a joint webinar with Robert Bosch Engineering and Business Solutions in India. The topic of today's webinar is on integrating PTV Vissim with a game engine, Unity3D, for carrying out driver behavioral studies. I would like to remind you to follow our LinkedIn page, PTV Group IMEA, to learn more about our upcoming webinars, online trainings, offerings, and more. During the second half of the webinar, we will be pushing a poll survey and we kindly ask you to participate. Allow me to introduce your team for this webinar. Our main presenter will be Caleb. He's the research lead, Intelligent Transportation System Group, Robert Bosch Engineering and Business Solutions in India, with a PhD in Transportation Systems Engineering from Indian Institute of Technology, Bombay. His experience revolves around research and consulting transportation systems, modeling and simulation, transportation system data collection methods and extraction algorithms, connected and autonomous vehicles, electric vehicles, behavioral sciences, and marketing forecasting. I'd like also to introduce Boleslav, our principal solution architect for modeling at PTV Group, with more than 15 years of industry experience in transport planning and forecasting. Boleslav is responsible for technical business development and innovation in Middle East, India, and Africa. He had played a key role in PTV Group's expansion in the region. He also leads knowledge expansion and training programs for PTV Software Suite. On the panel discussion, Prabhu, our transport modeler in PTV ARMIA, will also join us. He is responsible for delivering new mobility solutions for smooth, safe, and optimized route planning for movement of vehicles and goods in ARMIA region, which covers India, Middle East, and Africa. As a transport modeler and project manager, he's responsible for planning, analyzing, modeling, rolling out, and managing the project in-house and liaise with the client for delivering the project successfully. And myself, your moderator, Majd, from the marketing team here in Dubai. Before I hand over to the speaker, I would like to encourage you to type in any questions you have in the question box during the presentation, and we will address as much as possible in the dedicated Q&A session. A link of today's webinar will be sent out in a follow-up email by tomorrow. And that's all for now. With no further delay, I'd like to hand it over to you, Caleb, for a brief overview about the webinar.
Thanks, Mast, for the introduction. And I welcome all the participants who are taking part in this webinar. So the overview of this presentation would be in the following manner. A brief introduction would be there, and there would be details of the proposed integration framework, how we have integrated the simulator PTV Vissim with a game engine. Then there would be presented the implementation details, then how we have generated the trajectory data, using that data how and what analysis we have done for understanding the driver behavior, and beyond the driver behavior analysis and modeling aspects, how we have used such data for automotive applications is what we will see next. And it will finally conclude with some of the summary of the work that has been done and some conclusions that one can make. And finally we will have the poll questions and the Q&A session. Yeah, so let me start off with the introduction. Most of the times it's a very well-known fact for all the modelers, researchers, practitioners, and the solution builders. Having the micro-level trajectory data of drivers is very, very important, be it in the context of driver behavioral studies or be it in the context of developing automotive applications and beyond. But the major problem there is collecting and extracting such fine-grained trajectory data from the field is definitely a costly and a cumbersome affair. So then the question that we have at hand is there a way that we can build, let's say, a cost-effective data collection system that is in itself capable of creating all possible real-world traffic scenarios and then present it to the drivers who can drive in such scenarios and then see how they are responding to that particular scenario? If that is a question, then one of the answers that we can definitely say is that if we can gamify a microscopic traffic simulator where it allows a driver, an external real driver, to interact with the simulation interface that we have. Like for example, here in our case today, we are specifically talking about PTV Vissim, which is a good traffic simulator that can represent most of the traffic scenarios in various regions, so to say. So with this as the introduction, let me now get into the core part of it. So the basic idea is simple. When we have a traffic simulator like PTV Vissim, most of the times it is something like you can run the simulations, you can test out various traffic management strategies, signal control strategies, and then come to an understanding of how good those management strategies are. So, but the point here is when an external driver would like to jump into that scenario or the traffic simulation that we are running, that would not be a kind of an option that we normally do have. But if we want to have the driver in the loop, then it's for sure that we need to have an interface that can actually toggle the information, or maybe have the information exchange between the driver as well as the simulation environment that we are running. So that's basically the idea, where we can gamify a traffic simulator and allow a driver to play that as a game will definitely be a good option. So that's what you are seeing here in the picture that I have put here, where we talked about the tools integration part, where we have the traffic simulator, then we have a game engine, then we build a communication module so that it exchanges the information between the traffic simulator and the game engine. So the idea basically is, using this game engine interface, the external driver would be looking at the environment that we have created in the simulator, and then he or she would be driving in that particular environment that we have created, and we can understand how good the driver has driven, or how basically he or she has driven. So then going to the much fine grained implementation details, this is what exactly we do. We have the VISSIM, basically, which is the microscopic traffic simulator. Then we will start VISSIM, and if VISSIM is running, then we would like to import the layout that has been created in VISSIM. The layout could be in terms of the roadways that you have put as a part of the simulation model that you have built, the traffic signals that you have created, whatnot, all static and dynamic elements that you see on the roadway. Then we take that layout and then create the same layout in the game engine Unity3D. Then we have the external vehicle, that is nothing but the driver who is external to the simulation environment. That we will take and then send that vehicle data, which is external to the VISSIM traffic simulator, to VISSIM. Now, this data actually is combined with the traffic data that is already being generated in VISSIM. Then take that, both the information, and then we need to adjust the vehicles as per the data that we got both from the Unity game engine as well as the VISSIM traffic simulator. Then we have the user input that will be given by the driver who is driving using such a platform. Now we take that road users input and then update users vehicle position, and then we take that information to VISSIM, and similarly VISSIM vehicles information which are being controlled by the VISSIM simulator, we can also take that information and then put it in Unity. So in essence, what this flowchart is saying is, there is the information exchange that is happening between the game engine and the VISSIM traffic simulator. In terms of the actions that an external driver is doing, that will be taken as an input and will be shown in VISSIM how a particular driver has driven. And similarly, all the other vehicles which are surrounding this particular driver who is external to the environment will also be updated in the Unity game engine, and that will be shown to the driver who is actually interacting with the game engine. Then going into further details, this is where you will be able to see how to enable driving simulator interface. You need to go to the network settings and then enable this driving simulator active. This has to be done, and after that we basically have here, what I'm showing is some pieces of code that we have written in Unity using C#, and then trying to take that particular piece of code and trying to interact with the Vissim's driving simulator DLL. So this is what this piece of code is showing here. It is basically trying to connect Unity with Vissim's driving simulator DLL that is already available. And if people would like to have a know-how of how this can be done, even in Vissim, some of the example files, you will be able to see how this can be done. Then the second step is, once we have established the connection between Vissim and the Unity game engine, then we need to really start Vissim and then start running the simulation. So this piece of code is basically saying here how to start Vissim. Okay. Basically, that involves going to the traffic simulation model that we have built, which will be an INP file that would normally get created out of Vissim when we are building a model, and then take that into account and then start running the simulation. Then the second part of it is basically, as I already told, we need to read the static data from Vissim. So this is where you will be able to see how we can translate the elements that we have created in Vissim as 3D objects in Unity. So it will basically spawn different objects that we have created in the simulator, and then it will be showing up in the Unity 3D interface that we are going to show to the external driver. Then similarly, as much as static data is important, dynamic data is also very important. In terms of the road surface, the road texture, in terms of the vehicle's positions, and so on and so forth. So this is what I'm showing here on the right side. Normally the positions of the vehicle and the rotation and the scale at which we are projecting these objects can also be taken from the Vissim simulator, and then it can be shown in the game engine. Then we have a very important part where we want to translate the client's actions, whatever he or she is doing using the Unity interface, and then read that as the input and then take that input back to the Vissim simulator. This is important because at the end of the day, both these pieces of softwares or the tools have to talk to each other and then get information promptly and correctly, so that there is no mismatch between the Unity interface that the environment that we are showing in the Unity interface and the environment that is being simulated by Vissim. Both should be in unison. Then this is what exactly I was talking about. This two-way communication module that we had to build between Vissim and Unity is the heart of this whole project, I would say, which basically is trying to, again, I'm reiterating the fact that the data has to be exchanged promptly and correctly between both the pieces of the software. And that is where this driving simulator interface would really help us to make this exchange of information happen for us. It can include the vehicle data. It could, if you are seeing here in the piece of the code, you can see the vehicle data being transferred between both the software tools. Then it will also transfer the or exchange the pedestrian data. Then the signal data or the state of the signals can also be exchanged between both the tools. So here I would basically like to speak a few things of how the implementation that we have done has translated it into a product. So I will first show you this or give an explanation about this static pictures that I have put here, and then after that I would like to play a video as well. Okay. So here what you are seeing is on the left side, okay, in this picture that I'm showing on the left side, the left extreme side, are basically the interface that a normal driver would be seeing in Unity 3D or the game engine. And the one which is on the right side is basically showing the environment that you see in the traffic simulator Vissim. So just to give you an example how the implementation has worked out successfully is, if you see this first picture, there is a vehicle here which I have termed it as external driver controlled vehicle as seen in game engine Unity 3D. The same vehicle can also be seen here on the right side, where again I have put it as external driver controlled vehicle as seen in traffic simulator VISSIM. So both the vehicles are being shown here. Similarly, you have the VISSIM controlled vehicles which are actually interacting with the external driver vehicle, also shown here in Unity 3D. If you see the other vehicles, those vehicles are actually controlled by the VISSIM traffic simulator. And similar vehicles you can also see obviously in the traffic simulator VISSIM's interface, which is on the right side here. So as and when you are moving, you can also see in the second picture that the vehicle in Unity 3D has moved, and similarly you can obviously see that the same vehicle has moved in VISSIM simulator. But this VISSIM simulator vehicle that you are seeing here, okay, is actually whatever is being shown in VISSIM simulator. That vehicle's movements are controlled by the external driver who is trying to interact with the VISSIM environment using the game engine. So that is what these three pictures speak. And then I would like to show you a couple of uh, videos here. Uh, Let me know if you are able to must you are able to see the video.
Yes, it's showing now.
I'm
Yes.
Yeah, this is how the vehicle is moving. This is the external driver vehicle that it is moving. And this is how you are seeing the vehicles in VISSIM. And then again, I'm coming back to Unity 3D, where there is a vehicle movement that is happening by the external driver. And the same you can see it here, where this vehicle has moved from the intersection and then it has stopped. Because it has stopped, the VISSIM vehicles are also reacting to the driver's actions, who is external to the VISSIM environment. Now again, the external driver has moved. You can always see that movement again happening in VISSIM. Yes, now if you see, the vehicle has moved, and then all the other vehicles are also reacting to it. Yeah, I will play the second video as well, where in which you can actually see a real driver interacting with the game engine using the pedals as well as the steer wheel. uh, Must, are you able to see the video playing?
No.
Hello, I am actually playing it, but then uh, it's not showing.
No, it's not. Now it's showing.
Here you can see a real driver taking control of the Unity game engine vehicle and then trying to interact with the VISSIM environment. Okay, so I will go back to my screen now to show. Yeah, I think we are back to the presentation, right?
Yes.
Okay. So once we conduct such experiments, the typical outputs that we normally get out of the experiments that we conducted would be something like this, the table that I am showing here on the left side. It will give out the simulation second at which the vehicle was present in the simulation environment, and the vehicle number it shows, and then this third column is interesting because we have to know whether that particular vehicle is an external controlled vehicle or is that vehicle being controlled by VISSIM. So here if you see, it clearly shows EVC drive sim is basically the vehicle which is being controlled by an external driver, and wherever it is not, it is being controlled by VISSIM. And similarly, the most interesting and the most important aspect is to get the X and Y positions of these vehicles. So that is nothing but which is being shown in the last two columns. Position is the longitudinal position, and the last column values are nothing but the lateral positions of the vehicles. Just to show how this data can be used to plot the trajectories of the vehicles, I have just given an example here on the right side. uh, all the dotted lines are basically the VISSIM controlled vehicles, and the solid line trajectory is nothing but of the vehicle or the driver who is external to the VISSIM traffic simulator, who is interacting using the game engine. So now we can generate such data with different drivers, with different experiments, and so on and so forth. So typically we conducted experiments with different drivers, and then we have generated data using such platform, uh, which is basically the trajectory data that I'm showing here. The first top two diagrams are showing the longitudinal positions and the lateral positions of the drivers respectively in the two pictures here, which is nothing but the positions over time charts that I have put forth here. The second set of which are at the bottom, the second set of charts that I am showing here are nothing but the experiment which we have done at a signalized intersection. So you can clearly see that on the left bottom picture that the vehicles are stopping at a during the red signal, and then again starting to move once the signal is turning green. Similar would be the case when we are looking at the lateral positions of the vehicles at a signalized intersection. You can see the drivers taking a left turn, drivers moving straight, drivers taking a right turn. So these are just some typical examples of how the data can be generated. Using such data, we have actually done some analysis to understand the driver behavioral aspects. The first and foremost thing that normally people would be interested is in understanding the reaction times of the drivers. So there is a small methodology that we have followed here to extract the reaction time out of the trajectories that we got. Basically, if you look at the parameter reaction time, it's a latent variable. Most of the times it is unobservable, and it's very difficult to extract such reaction time in the real field, even after getting the trajectories, right? So what we basically assumed, or the assumption basically is that, which is a valid assumption, that the acceleration of a driver, okay, uh, would be in response to the relative speed between his or her vehicle and the vehicle which is in front of it. Basically a basic car following model, what we can call it as, or the car following theory, that a particular action of the following vehicle would be in response to the speed of that particular vehicle and the vehicle which is in front of him or her, which is basically the leader vehicle. So, and after having certain reaction, after taking up some reaction time, the reaction can be observed in terms of how much acceleration or deceleration a particular driver has done. So if you look at the first plot here, okay, first we started off assuming that there is a particular reaction time, okay, that a normal driver would take. Let's assume that we are starting with 0.5 seconds as the reaction time. Taking that reaction time into account, we have plotted what is the correlation between the relative speed and acceleration. That's what this first graph shows. And then we looked at how much they are correlated by looking at let's say r square value, okay. that is showing us 0.5, around 0.5, right? And then the second chart, basically we have assumed the reaction time, let's say, to be 1 second. Then how is the correlation changing? Then similarly, we went maybe to a higher reaction time, let's say 2 seconds or 3 seconds. Okay, so that is what the third graph is showing. If you see or look at the pattern, okay, in which this correlation is getting changed, there is one particular value where we are seeing a high correlation between the relative speed and the acceleration. So that is one time, whatever we are looking where there is high reaction time, is what we would like to conclude as the reaction time of the driver. So just to give you a more clearer picture from the data that we have got, we can clearly see here the plot between the reaction time and the adjusted square. Here, if you see in this plot, around 0.8 seconds of reaction time, you can see that r square value has the highest value, or r square has the highest value. So that's where we take that to be the reaction time of that particular driver. Okay, so that way, for every driver from the trajectories of the leader vehicle as well as the follower vehicle, we need to do this experiment and then understand what is that reaction time at which there is high correlation that is existing between the reaction between the relative speed and the acceleration or the deceleration. So this reaction time can vary for each driver. Okay, so the density plots, once we got the reaction times of different drivers, we have plotted here. And we also made sure that the drivers are driving different types of the vehicles uh, when they want to take control of one of the vehicles in Vissim. If it is two-wheeler, if it is car, if it is truck, and so on and so forth. Here it would be clearly understood, okay, once you are seeing this density plot, where we clearly understand that the two-wheelers are more aggressive in nature, and that's why their reaction times are quite less compared to cars or trucks. But at the same time, if you look at the behavioral aspects of the two-wheeler drivers, they will have a huge spread, okay, when we look at the reaction times of the two-wheeler drivers, because every two-wheeler driver will drive in their own way, so to say, right? But as and when you see that the vehicle sizes are increasing because of the constraints that would normally come up with the dynamic characteristics of the vehicles and the static characteristics, that's where the spread would be much lesser and lesser. That's what it is being clearly shown here in this plot, where in which we are talking about the two-wheeler drivers, car drivers, and truck drivers. So the second parameter and the third which we took into account are basically the space headways and time to collision. The same story repeats, that the headways that are normally followed by two-wheelers are less compared to cars and trucks, but the spread of that space headways is much higher in two-wheeler drivers. Okay, similarly, time to collision, the same story repeats. So that's the conclusion that we can make with respect to these two parameters. And similarly, in lane change duration, you can clearly see that the two-wheelers are taking lesser lane change time. Basically, the lane change duration can be defined as the time taken for a particular driver or a vehicle to move from center of one lane to the center of the other lane. Similarly, we can also talk about the gap acceptance that normally people would be interested in, to look at what are the gaps that are being accepted by different vehicle type drivers like two-wheelers, cars, trucks. Again, you can see that two-wheelers are always comfortable accepting lesser gaps, but cars want a bit higher gaps, and trucks definitely, because of the safety concerns that they would have in maneuvering that larger vehicle, they will need much more time for changing the lanes. So now, taking those parameters, and then we have done some statistical tests, and out of such data that we have generated, we also built different driver behavioral models. Here, basically, the first table is showing some statistical test results. Basically, we call that as analysis of variance test, where the null hypothesis is firstly assumed that uh, there is no difference between the driving behaviors of different vehicle type drivers. But all across these parameters, we can clearly see that the null hypothesis got rejected, so to say, which is telling us to accept or to go to a inference that yes, definitely there is a very strong effect of the vehicle type on the driving behaviors all across the parameters that we have taken here and analyzed. Similarly, for each of these driver behavioral or the driving behaviors, we have also fitted the probabilistic model or the distributions, and the best of the distributions were selected looking at the k statistic value, and also the parameters of each of these distributions. For example, if we take the reaction time, the reaction times were following the log normal distribution, and obviously the model parameters are the mu and sigma, which are the mean and variance, and similarly k statistic will tell us whether it's a good fit or not. So the same thing repeats for the space headways, the time to collisions, lane change durations, and gap acceptance at unsynchronized intersections. So all in all, here as a summary, if we want to talk about how the trajectory data can be used to understand various driver behaviors and to build the driver behavioral models, this would be a very good example that somebody can talk about of how the data that is being generated out of the driving simulator can be used to understand the driving behaviors of the people or the drivers. Now, beyond driving behavioral modeling and let's say the analysis that we can do, there is something else that we can also do, especially in terms of the automotive applications. So we know that sometime in the future we will be hitting a point where we see all autonomous vehicles flying on the roads. And the major important aspects, other than, of course, there are different other aspects which are very important for autonomous vehicles, starting from perception that has to be there for an autonomous vehicle. Then they need to get that information out of that perception algorithms. Then they take those algorithms and then start making the autonomous vehicle understand the surrounding environment and then do the actions by itself in terms of whether to accelerate, decelerate, if it has to accelerate, how much to accelerate, whether it has to decelerate, how much to decelerate, whether it has to take a decision to change to the other lane, whether it has to avoid the collision, and so on and so forth. So in essence, what we can say is autonomous vehicle is no more than a virtual human being. So if autonomous vehicle has a brain, which a normal human being has, then the autonomous vehicle can itself drive. So that is what we normally call it as like the path planning by an autonomous vehicle. And as I have already talked and said that autonomous vehicle is no more than a virtual human being, then it's quite obvious that we will come to a logical conclusion saying that the autonomous vehicles can always learn from the real human drivers how to drive by themselves. So that is where we can take these trajectories that we have generated out of drivers in that particular environment. And of course, in that same environment, if we want to make these autonomous vehicles learn of how a particular driver or in general the drivers would behave, it would be fantastic, so that autonomous vehicles can learn from human beings. So that's why this name comes, which is called as imitation learning, that I have put here. The basic core idea is the autonomous vehicle or the autonomous agent is trying to learn from the expert driver and trying to replicate or follow what a particular driver has done. So here you can see on the plots that I have shown here in terms of how we can make the autonomous vehicle learn different steering angles in terms of how a real driver has driven. And what you are seeing at the bottom left as the plots are nothing but the lateral positions that the autonomous vehicle has learned from the drivers, and it shows what was the actual trajectory that a real driver has taken in terms of lateral position, and then what was being predicted or being used by the autonomous agent. So this is just another example where we can use such trajectory data to train autonomous vehicles and make them imitate what a driver would do in a particular situation or an expert driver would do. So here I would like to again play another video. uh, must let me know once it starts playing. Yeah.
Yes, it's showing now.
Is it playing?
Yes, yes. It's showing now on the screens. It's playing.
Great, great, great. So what you are seeing here on the left side is an expert driver, how the driver is driving, and on the right side you can see the autonomous agent also driving similarly what and how the driver is driving. So this particular thing was implemented in an open source autonomous vehicle simulator which is called Udacity. But of course the data that we have used was from the trajectories that we have generated out of the platform that we have. Okay, so this is one lap of driving that we have shown here, but we have several such laps that we can show in different environments. Okay, yeah, so let me stop the video here and then go back to the screen. Okay, fine. So I am back to the presentation now. Similarly, another application where we can actually use such trajectory data is in understanding the emissions, how a particular driving behavior has impacted the emissions that can come out of the vehicles. So we have used a particular model which will take into account the speed of the vehicle and accordingly predict the emissions using some emission factors. So if you see here, the first plot on the left is actually showing the CO emissions, which is in grams per hour, depending upon the speed of that particular vehicle. And you can clearly see that there is a strong correlation between the speed of the vehicle and the emissions that are getting emitted. So this was basically with respect to a uninterrupted traffic flow section of a road. On the right side at the top is basically the plot which is showing the emissions data of a particular vehicle where it is trying to maneuver a traffic signal. So that's why you can see the stoppage and then again going forward with respect to the speed, and then the emissions also increase. The third one is basically the emissions data that has been generated from an experiment where there was an unsignalized intersection and how a driver has maneuvered through it, and then using that speed data how the CO emissions can be predicted. Okay, then yeah, finally to conclude we can say that the driving simulator interface in PTV Vissim definitely provides a nice opportunity for developing one's own driving or vehicle data generation platform. Okay, then as we have seen with respect to different applications that I have shown, definitely such data platform generation platforms will be useful for conducting driver behavioral studies and obviously developing automotive applications. As far as our experience is concerned, here we can say that the platform developed in the present study definitely helped us quite a lot in understanding the driver behavioral aspects, and going beyond the traditional driver behavioral modeling aspects, we can also use such models or the data that we are getting out of that platform to develop automotive applications. Yeah, so I think this is what all I have to say as far as the presentation is concerned.
Yeah, thank you, Caleb. Boleslav is here. This was actually
and of course I would definitely like to acknowledge the work that my former intern students have done. Yeah. Go. Hello.
thank you, Caleb. That was hello. Can you hear us?
Yes, Boleslav, we can hear you clearly.
Yes, yeah. I am able to hear you. Please go ahead.
Okay, great. Yeah, that was really an exciting session. I think many of us never tried it on our own. However, It's a well-known module of PTV Vissim software package, which is called Driving Simulator, that allows to perform such kind of research exercises. Yeah, and you highlighted quite a lot of use cases today, and from our perspective, we know quite a lot of applications in a similar direction, however, not with the real drivers, but with autonomous vehicles. This is also one of the use cases where driving simulator is used, where the actual autonomous vehicle is plugged into VISSIM simulation and it gets some information about the simulated vehicles to inform its own behavior and reactions. So the purpose of this type of a use case is slightly different. It's more to calibrate the autonomous algorithms rather than to calibrate the behavior within VISSIM. Yeah, but this is also a very interesting use case. And actually, while listening to you, I was thinking about possibilities for wider applications for this. And Caleb, what do you think about application of this type of a solution in driving schools, for example, with the existing driving simulators? Because I understand this was a research type of an exercise. However, bringing it to real life of driving institutions could expand the capabilities of their own existing driving simulators, or can become a basis for data collections for the traffic studies, because they already have all the hardware necessary to implement the solution.
Yes, I would like to answer that question, Boleslav. Yeah, good question, definitely. Yeah, so as Boleslav has very nicely put together different thoughts wherein which we can explore more areas of applications or the use cases using such platform. It's for sure that we can use, let's say, for example, in the driving schools where, or for that matter, even to issue licenses for the people, okay, to first of all, to create complex environments and then see or evaluate their driving skills. That's definitely one of the use cases we can immediately talk about, and then see that many people can come and drive in a virtual platform like this, and then we can get the trajectories of those people and then evaluate some of the driver behavioral aspects that we have talked about in terms of how safely they have driven, for example, time to collision, and how smoothly they have maneuvered a particular situation that we have given to them. So definitely, yes, that would be one of the use cases. And also I think in most of the driving schools people are trained to drive, okay, using such simulators. So that is one more use case where we can say that, okay, fine, we can use such platforms to make people learn how to drive better, or how to improve their driving behaviors. The third other important application that I can also think about, Boleslav, is that here, if we can actually come up with a good hardware setup, okay, let's say for example in terms of an electric vehicle setup, okay, right now we have just shown the setup in terms of gear wheel and the uh, pedals, right? But if we can have the whole of the hardware that we can fit into a kind of a digital twin that we want to create in a laboratory for a whole vehicle itself, okay, and in that respect, if we can have the hardware that represents the powertrain, let's say, of electric vehicles, and the battery being fitted into that, we can also try out understanding how the driving behavior of an electric vehicle when he or she is driving that electric vehicle, because of the driving behavior that they exhibit, how it is deteriorating the battery performance in one sense. So that could be one more important aspect where we definitely want to test out how the driving behaviors are exactly, or how they are trying to influence the battery performance. Because as we all know, one of the major hurdles that we have with electric vehicles is the range anxiety, and how the discharge characteristics of the battery is or are varying, right? So if we can have a very good hardware setup which can represent the actual vehicle in the field, then it's just not making the drivers to learn or evaluate the drivers, but we can actually do some sort of predictive analytics when such next generation vehicular systems are coming into picture. So you see what I'm saying, right, Boleslav? The driving behavior would definitely, but the whole crux lies in building that whole vehicular system, which is exactly the representation of the real vehicle in the field. Hope I have given enough directions here as far as the other applications are concerned, where we can talk about.
Yeah, thank you, Caleb. Look, I see that the audience already started posting questions, and this is really good. I want to encourage all of you to write any type of questions if you have. And before we'll continue with the questions, I would like actually to ask one question to the audience about the use cases for this type of a solution. And for that, I would like to push out one poll question. So as we discussed, there are, let's say, two big chunks of use cases for this type of a solution. And one of them we think is about the data collection for research and VISSIM behavior models calibration, as well as the second one for automotive applications. Or maybe you can think of some other use case. What do you think, what is the most relevant field of application of such solution in your daily work? Please feel free to give your opinion to this question, and you should be able to see the quick poll on your screen where you can choose one of the answers. Yeah, thank you very much for taking part in this quick poll. And actually what I see is that 80% of the audience is interested in actually collecting the data for driving behavior. And yeah, this is really a well-known use case, which is used by many consultants. We also had experience with the similar studies, however, not touching upon Unity, and that is why actually we invited for this webinar Caleb, because in our region there are clients who are really interested in calibrating driving behavior for their studies. However, the number of solutions, cases, and possible options to do it, it's not very well highlighted. So yeah, thank you very much. At this stage, I would like to close the poll, and let's continue with the questions. There is one question that we've got, and this is the question: can this process be used for digital twin projects? I didn't really fully get what it means by the digital twin here.
Yeah, so Boleslav, I can take that question and then answer it if it is fine by the audience. Yeah, sure. Basically, what they are trying to say here is, as we have shown, let's say, for example, just with respect to the steer wheel and the pedals, right? And as I've already explained at the end, wherein which we can expand the use cases. So basically they're talking about, I suppose, the assuming that we actually have the exact vehicle that we are seeing in the field and with a digital twin of that in a laboratory setup. So basically what it is, we are seeing in field will be presented using VISSIM. Similarly, the driver who has to interact with that particular environment is also there. So the third part to actually create such a digital twin is to set up the whole of the vehicular system itself, exactly how it looks in the real world. So it's a kind of our own driving simulator that we have put in, but then with a lot of reality that we want to build into the vehicular system itself, how exactly the driver feels when he is in the field or she is in the field and then driving a real vehicle. So I suppose that that's what the question is indicating to. Yes, definitely, as long as we have very good hardware being set up around this particular experimental platform, definitely we can develop our own digital twin of a particular vehicle that we want to develop for. Yes, Boleslav, you might want to add some thoughts onto it. Please go ahead.
Yeah, I think that actually covers. What I also wanted to ask is what was the sample size that you were using for this study? Number of experiments that you did.
Correct. So with respect to the sample size, it varied with respect to the vehicle type that we have taken into account. Basically, with respect to different vehicle types, I think two-wheelers were higher in number, were around 200 people. Okay. And then for cars, it was around 150, and then trucks, some 80 to 90 people who have driven. Yeah, these are all the people whom I know and ask them to drive using such platform. Yeah.
Okay, okay. Okay, and we've got one more question. How did you modify the hardware setup for different vehicle types?
So basically, that's a good question, because that's one of the limitations. Because be it the two-wheeler or the truck might be a similar case, but with respect to two-wheeler, we just use the keyboard switches because we did not have the hardware that has been set up for two-wheelers. So basically, with respect to keyboard switches, also like we normally play a game, right? So we can use those switches and then we can play it as a game and then we can get the data out of it. So, but it's a very important question because the hardware that has to be set up for these different vehicle types will definitely influence the behavior of the drivers as well.
Yeah. So in fact, yeah, this is, let's say, a software part of things. However, hardware component is quite important. So it's really necessary to find a good platform for this type of experiments. However, if it is in place, a lot of data can be generated. And just from my experience, we were discussing with one of our clients just about a year ago how to calibrate VISSIM behavior model. They were really interested to obtain information on the VISSIM behavior, country specific. And at that stage, most of the discussions were going around doing a drone video recordings, generating trajectories out of that, and then deriving some parameters for the driving behavior model. However, this use case, I think, can complement with regards to the parameters such as reaction time, which is not so easy to obtain out of the drone data. So this is a complementary solution. We've got one more question. What was your approach for data collection for the project?
The process of data collection, basically we have the drivers in place who will be driving with respect to the scenarios that we have given, and the data collection, the best part of this whole platform is once the driving simulator experiment is done, the data would itself get logged into the output file that we normally get from VISSIM. Okay. So that's one of the example file that I have shown. I have placed it in one of the slides, and I have clearly shown how the positions of different people who has driven in that particular environment are already automatically getting logged in by VISSIM itself. So that's the best part of it. So once we have such data, we can always look at that Excel or the output file and then see which was external driver and which was not, and we can actually take that external driver's data, and then that is how we generate the trajectories. So that's the answer that I would like to give for the question how the data was actually collected.
Okay, so just to add to that, so to generalize, it means you need like to perform such kind of a research, you would need to identify a set of drivers, you need to define for them a set of also instructions, what actually will be the route that they will be driving within the simulation, maybe
Correct.
some instructions with regards to the speed limits and so on. And actually they perform several drives in the simulation, each driver, so that you can get enough data to generalize it. Yeah, and obtaining
Correct.
results is nothing else than just using VISSIM evaluation results.
Right.
Okay. Yeah, very nice. It looks like we are done with all the questions. So then I think we can close this webinar. This was really one of the very interesting sessions, and we would like to welcome Caleb to maybe one of our next webinars with the follow-up steps on this. We would be closely watching on the progress, because this is really some interesting topic for the region. Thank you very much for sharing this information with us, and any one of you who were listening to the webinar, if you're interested to get some more details or get a feel and touch of this information, feel free to get in contact with us, and I think Caleb will be happy to share maybe some extra details or have some follow-ups after the webinar.
Sure.
So, yeah, thank you very much.
On a concluding note, I would also like to thank all the participants who have participated in this webinar, PTV for enabling such platform, and of course my own organization here, Robert Bosch, who supports me in most of the endeavors that I would like to pursue. Yeah, thank you all.
Thank you, everyone. Thank you for attending. A reminder of the recording will be circulated for all attendees, so you'll be able to get back to it in case you have any questions, any vagues about the later session. In case you have any further questions, please contact us on sales.imea@ptvgroup.com, and looking forward to seeing you next time. Thank you, Caleb. Thank you, Balaslav. Thank you, everyone, for attending.
Thank you.
Sure. Thank you.